Hi, this is Dr. O'Connor. In this video, we're going to go over Chapter 24. Now, there are quite a few sections in 24 that you don't need to read, so make sure you look at the module organizer and follow along with this video. This video will let you know which sections you need to read. So follow the video and then go to those corresponding sections in your textbook. Anyway, we're going to talk about carboxylic acids and esters in this video. And carboxylic acids are compounds that have a carbonyl group bonded to a carbon atom and an OH group or a hydroxyl group. So the most common carboxylic acid that you are familiar with would be acetic acid. And that looks like this. Okay, so here we have the carboxyl group. The other common carboxylic acid that you're familiar with is citric acid, and that's this molecule here. And it's quite a lot larger than the acetic acid, but again, here is the carboxyl group. Remember, it's this hydrogen here that is the acidic hydrogen, okay, the one that's bonded to the oxygen. These other hydrogens are not. So let's also define what an ester is. An ester is a compound that has a carbonyl group bonded to a carbon atom and this OR group, or this alkoxy group, if you will. So an example of an ester would be something like this. Let me move this over. So we have, let's say, this here, and so we have the carbonyl group. So carbonyl carbon then is bonded to this oxygen here, and then there's another alkyl group. So this part here, okay. Esters are synthesized from carboxylic acids and alcohol. So a carboxylic acid will react with an alcohol. So this part of the molecule here comes from the alcohol, and this part here comes from the carboxylic acid. So you can make a variety of different compounds depending on the carboxylic acid you start with and the alcohol you start with. We'll get into that in a little bit, okay? So again, carboxylic acids have the carboxyl group. That's the carbonyl group where carbonyl carbon bonded to the OH. An ester is a carbonyl group where carbonyl carbon is bonded to an oxygen, and this oxygen is bonded to this alkyl group, or some organic group. Now, we're not going to talk about amides here, but I am going to show you what they are. We have a carbonyl group, and carbonyl carbon is bonded to a nitrogen. We'll talk about amides in a later section, but I think it's a good idea to introduce them here because carboxylic acids, esters, and amides all have one thing in common. Carbonyl carbon is bonded to another electronegative atom. In the case of carboxylic acids and esters, it's bonded to an oxygen. In the case of an amide, a nitrogen. So this means that these types of compounds undergo different reactions than do the aldehydes and ketones. Remember, aldehydes and ketones undergo the addition reaction. So in other words, the carbon-oxygen double bond is partially broken, whereas carboxylic acids, esters, and amides undergo carbonyl group substitution reactions. So in other words, this group here, sorry about that. This group here is substituted by another group. As you can see, carboxylic acids and their derivatives. By the derivatives, we're talking about esters and amides. They all contain a polar functional group. That means they're higher boiling than similar molecular weight alkanes. In fact, carboxylic acids are higher boiling than alcohols with similar molecular weights, and that's because of that hydrogen bonding. As I said, carboxylic acids and esters and amides all participate in carbonyl group substitution reactions. So as I said, the group bonded to the carbonyl carbon is replaced by some other group. And one more thing you need to know, an acyl group is this group here. So that would be, for example, let's do a compound here. So here we have our carboxylic acid. Okay, so our acyl group is this group here. Okay, so that's the part that does not change during a chemical reaction. So we'll talk more about that in a minute. So as you can guess, carboxylic acids, they behave as acids. The hydrogen of the carboxyl group is donated to bases. Remember, acids donate a proton, so that hydrogen is donated as a proton. And just like acid-base reactions, there is an acid-base equilibrium that's established in aqueous solutions. So you really need to maybe review acid-base reactions. Carboxylic acids can form hydrogen bonds with one another. So again, they're high boiling. They're actually higher boiling than alcohols with similar molecular weights. Carboxylic acids, up to 4 carbons, are very water soluble. And water solubility, just like with some of the other compounds we've looked at, will lessen as the size of the hydrophobic, remember hydrophobic, water-fearing, that's the hydrocarbon chain. So the water solubility will lessen as the size of the hydrophobic alkane-like portion increases relative to the size of the carboxyl group. Straight chain groups up to 9 carbon atoms are volatile liquids, and they have sharp odors. Acids that have very long saturated groups are odorless and waxy solids. Actually, we'll talk about these when we get into the biochemistry. For example, fatty acids are carboxylic acids, but they have very long carbon chains, 16, 18, 20 carbon atoms. So they are solids, and again, they're waxy solids, and they're not water soluble. We're going to name some carboxylic acids, and basically what you do is name as an alkane, replace the E with oic and acid. So if substituents are present, you number the chain nearest the carboxyl group. Carboxyl group is always carbon number 1. So this one here, we have a 3-carbon acid. This would be called propanoic acid. This one here, again, we start numbering at the carboxyl group. So that's 1, 2, 3, 4. That's a butanoic acid. And on carbon number 3, we have a methyl group. This is 3-methyl butanoic acid. Here's one here. It's, notice it has both a carboxyl group and an OH group. So this is called lactic acid. That is the common name. And we're going to be dealing with this when we get into the biochemistry. We'll actually come across this over and over again. But its IUPAC name would be 2-hydroxypropanoic acid. So the acid has priority over the alcohol. So we have a 1, 2, 3 carbon acid. So that's propanoic acid. And there's an OH group on, actually that OH group should be on the carbon, on carbon number 2. So remember, the OH group is named as a hydroxy, so 2-hydroxypropanoic acid. Lactic acid is present in sour milk. It's also called milk acid. Also, when you exercise, sometimes lactate is produced faster than it can be removed, and that results in those muscle aches after intense exercise. Also, lactic acid is known as AHA in the cosmetics industry, and it's used as an anti-aging chemical that claims to make everyone look young by reducing those wrinkles. And it's, other acids are also used in the cosmetics industry for the same reason. It smooths out the fine lines. And then it's also used in food products in order to regulate the acidity of a particular food. Most carboxylic acids are known by their common names, and here are some other carboxylic acids that have other functional groups associated with them. So for example, here we have a carboxylic acid. Here's the carboxyl group, but here we also have this ketone-like group. And what we do is we label the carbons as alpha and beta. So the carbon adjacent to the carboxyl carbon is the alpha, and then the carbon, the second carbon here is the beta carbon. So in this case here, we have a 3-carbon carboxylic acid. This would be propanoic acid, but we have this keto group, remember the ketone, on the alpha carbon, so alpha ketopropanoic acid. This is also called pyruvic acid, and we will be dealing a lot with this one when we get to metabolism. Here's another example. Again, we have the carboxyl group. That's carbon number 1. Here's our alpha carbon, our beta carbon, and here we have an amino group. So we would name this again as a propanoic acid, and on the alpha carbon we have an amino group, so alpha aminopropanoic acid. And we'll again, we're going to come across these two acids a little later when we get into the biochemistry. What did we just do? We just went back to our first slide. Okay, here's a table that shows some of the physical properties of some of the carboxylic acids. And so here, the simplest is formic acid. It has a hydrogen bonded to the carboxyl carbon. Of course, acetic acid, propanoic, and so on. And here we can see the boiling points. And we see the boiling points increase with the number of carbons. Okay. In a minute, I'll show you what dicarboxylic acids look like. I mean, those are obviously acids, right, that have 2 carboxyl groups. And we also have unsaturated carboxylic acids, so that's where we'll see a carbon-carbon double bond. So acrylic is one of those acids. And, of course, the aromatic acid. This first one is called benzoic acid. And this one here is salicylic acid. And we'll talk about some of these in a little bit. The acyl group that remains when a carboxylic acid loses the hydroxide group is named by replacing the IC with an OYL. The only exception is the acyl group from acetic acid. We refer to this as an acetyl group, as you'll see later when we get to the citric acid cycle. So this obviously is the acyl group from acetic acid. We refer to this as an acetyl group. And then this would be from propanoic acid. This is a propanoyl group, so replace the IC with the OYL. And then this would be from benzoic acid, and we replace the IC with the OYL, so this is the benzoyl group. Next, we have dicarbolic acids that contain 2 carboxyl groups. So the first one is oxalic acid, and its IUPAC name would be ethane dioic acid. So note here the 2 carboxyl groups. And this is a stronger acid than acetic acid. Remember, acetic acid has a Ka of 10 to the negative 5. We find oxalic acid in things like spinach and rhubarb, and people that have kidney stone problems have to be careful when they eat these foods, because when oxalate combines with calcium ion, then you end up with kidney stones, so calcium oxalate, which is not water soluble. The next dicarbolic acid is succinic acid, and the IUPAC name would be butane dioic acid. And the reason for that is you have 1, 2, 3, 4. Remember, that carboxyl group always has to be at the end of the molecule. So we have 4 carbons, So that'd be a butane, and then the 2 carboxyl groups, that's the dioic, and then we add the word acid. This we will come across again when we get to the citric acid cycle. And then we have another one. This is acrylic acid. We saw it in that table. And this is called 2-propenoic acid, the EN, because of the carbon-carbon double bond. And this is used in the manufacture of paints and adhesives and, of course, plastics. So here we're asked to draw the structures for 3-methyl hexanoic acid. So I would go ahead and draw the 6-carbon chain that includes the carboxyl group here. Remember, the carboxyl group is always carbon 1. Then we go 2, 3. We have a methyl group on carbon 3. So this is the structure here for 3-methyl hexanoic acid. Next, they want a structure for ortho nitrobenzoic acid. So we know that we have a benzene ring, like here, and it's a nitrobenzoic acid. So there's our nitro group, and that means the carboxyl group is ortho with respect to the nitro group. So this would be ortho nitrobenzoic acid. So now let's take a look at the esters. And you can think of an ester as being a carboxylic acid where the OH is replaced with this OR group, or an alkoxy group. Esters are lower boiling than acids from which they are derived. Why is that? That's because esters do not experience intermolecular hydrogen bonding. Okay, so let's go ahead and name some esters. Esters names are composed of 2 words. The first name is the alkyl group in the ester group, and the second is the name of the parent acid with the IC replaced by ATE. So let's go ahead and take a look at this one here. So what we have here, remember what I said, that esters are made from carboxylic acids reacting with an alcohol. This portion here that contains the oxygen is from the alcohol, and then this portion here is from the acid. So we have a 1, 2, 3, 4 acid, 4-carbon acid. So that's going to be a butanoate. Or, well, let's go back a minute. That would be a butanoic acid. We replace the IC with an ATE, so that's butanoate. And this, then, we would name as the ethyl. So ethyl butanoate. This is the common name here. Let's take a look at benzoic acid. Remember, benzoic acid, sorry, my drawings are not the greatest, looks like this, okay? So here we have this portion here from the benzoic acid, so that would become a benzoate, and then this portion here would come from the alcohol, and that's a 3-carbon, so that would be propyl benzoate. Let's take a look at this one down here. And here we have, again, an ester. We know it's an ester because we have a carbonyl group and this oxygen bonded to carbonyl carbon. We have this alkoxy group bonded to carbonyl carbon. So again, I pick out which is derived from the acid. That'd be this part, okay? So this would have been 1, 2, 3, 4, 5. So that's a pentanoic acid. So a 4-methyl pentanoic acid. Change the IC to an 8. So we have 4-methyl pentanoate. And here we have this methyl group. So this part here contains a methyl group. So that's methyl, 4-methyl pentanoate, an ester. Practice naming these compounds, carboxylic acids and esters. Esters are lower boiling than carboxylic acids, and that's because they again, do not experience intermolecular hydrogen bonding. Simple esters, meaning smaller esters, are colorless. They are very volatile, and they have, some say, pleasant fruity odors. I never cared for the odors of them. They're very fragrant, and they usually smell very sweet, like flowers and fruit. The vapors, though, can have a narcotic effect. I know we used to use esters in one of our labs, and I would always be dizzy afterwards. Not a nice feeling. And lower molecular weight esters can be somewhat water soluble and also flammable. Esters are not very interesting because they do not act as either acids or bases in aqueous solutions. So let's go ahead and take a look at some common carboxylic acids. Formic acid has this formula here. And those stinging ants, well, that sting that you feel, that's the chemical that's responsible for the sting. It's the formic acid. Acetic acid, we all know that we find acetic acid in vinegar. And butyric acid, if any of you have ever left butter out on a hot day or overnight, you can smell it. It gets rancid. So butyric acid is responsible for that. Caproic acid, you might not be so familiar with, but this has a very distinct odor and was first isolated from the skin of goats. And then there's citric acid, and that's present in citrus fruits and blood. In fact, citric acid, I believe I had the, I showed you the structure for citric acid right here. And that's it. And we find that in fruits. It's all kinds of uses for citric acid. You'll find it in cosmetic, pharmaceuticals, foods, and so on. It's very nice because it adds a tartness to drinks and sweets. And also here, I want to show you another acid. This is the formula here for stearic acid. And look at it, very long hydrocarbon chain. And then we have this little carboxyl group here. This is a fatty acid. We are not going to talk about fatty acids and glycerol until we get into the metabolism portion. So that's going to be in a few weeks. So you don't need to read about glycerol and the fatty acids. Some interesting carboxylic acids are found in skincare products. So for example, the alpha hydroxy acids. So this would be an example here, or a general structure for an alpha hydroxy acid. Again, here is the carboxyl group, and the carbon adjacent to that is the alpha carbon, and the hydroxyl group is bonded to the alpha carbon. So this is an alpha hydroxy acid. So basically, these are supposed to make you look beautiful. They remove the outer layer of the skin cells, hopefully revealing healthier skin cells underneath. Now, let's take a look at a couple of other ones. I might ask you about some of these examples, okay? Aspirin is a member of a group of drugs called salicylates, and aspirin is very unique in that it is an analgesic, which means it relieves pain. It's an antipyretic, which means it reduces fever, and it's an anti-inflammatory, meaning it reduces inflammation. And one other use for aspirin is that of making the blood thinner for people that are susceptible to clots or people that are heart attack risks. They take an aspirin a day and it keeps the blood nice and thin. The only couple of problems with that, number one, if you take aspirin on a daily basis, there's going to be some bleeding. And number two, you have to make sure that you cease all use of aspirin before having any type of surgery. Otherwise, it's going to be almost impossible to stop the bleeding. This here is the chemical structure, and I see several structures here. we see the carboxyl group here, and we also have this ester group. Okay, so salicylates are what we call esters of salicylic acid. How do pain relievers work? I'm not going to go into a lot of detail, but what they do is they block the synthesis of these substances called prostaglandins. And these prostaglandins are responsible for our pain response. So we will talk more about this reaction later in the biochemistry, but that's basically how it works. It just blocks the synthesis of these compounds. As I said before, carboxylic acids are weak acids, and most of the carboxylic acids, except for a few, are about the same strength as acetic acid with Kas of 10 to the negative 5. One of the exceptions would be trichloroacetic acid, and this one, it is about 10 to the negative 1, making it a pretty strong acid. But most of your carboxylic acids, most of the ones that we're going to be working with, again, about 10 to the negative 5 for an acid dissociation constant. What happens when we put acetic acid into water, we've seen this many times, an equilibrium is set up, and what we have is acetate and hydronium ion. Remember what happens here. The acetic acid is a proton donor. It donates the proton to the water molecule. So therefore, in this case, water acts as a base, and it accepts the proton to become hydronium ion. And here we're left with the negatively charged acetate ion. So remember, acetic acid is a weak acid. So in this reaction mixture, you're going to have much more acetic acid than you do acetate ion, because it does not completely dissociate. Carboxylic acids undergo neutralization reactions with bases like sodium hydroxide. And remember, a neutralization reaction, the product is water and salt. So again, what we have here is we have acetic acid with sodium hydroxide. Remember, sodium hydroxide completely dissociates to sodium ion and hydroxide ion in aqueous medium. And again, the hydroxide ion will pick up a proton to form water, and what we're left with is the salt sodium acetate. So make sure you familiarize yourself with these acid-base reactions. We sometimes take advantage of the solubility of sodium and potassium salts of carboxylic acids. Remember, if we have a carboxylic acid that has more than 4 carbons, it's not going to be as soluble in water as acetic acid or propanoic acid. So what we can do is we can administer these carboxylic acids as sodium and potassium salts. So even though you might have a large hydrocarbon chain, they will be soluble in water when they're administered as salts. That's very nice. We can use the salts, which increases the solubility of a particular acid. So how do we name the metal salts of carboxylate ions? Remember, this part here, okay, this is a carboxylate ion, okay? So here we have, this one comes from acetic acid, and as we know, this is acetate ion, and we just name it with the metal name first and the anion name. In this case, we have sodium acetate. Notice it's not written with the metal in front. Sometimes you'll see that. We'll see the anion and then the metal, but we still name it with the metal name first. So sodium acetate. This one here, we have potassium, and this is a 1, 2, 3. That's from propanoic acid. So minus the hydrogen, it's a propanoate. So this would be potassium propanoate. So you want to practice some of those as well. Let's take a look at what happens when an ester is formed. Okay, so we always start off with some carboxylic acid, and it's that hydroxyl group and the carboxylic acid that is substituted with another group. So let's see what happens. First, ester formation from a carboxylic acid is called esterification. And what happens is we react a carboxylic acid with an alcohol to produce an ester and, of course, water. So let's take a look at this esterification reaction. Here we have butanoic acid, and here we have ethanol. What's going to happen is this bond breaks, hydroxide ion and the hydrogen will form water, and then a bond will form between the oxygen from the alcohol and the carbonyl group on the acid. So here is that bond formation. This one here is called ethyl butanoate. It smells like pineapple. It smells really good. So remember, this part here is from the alcohol. This part here is from the acid. For example, so let's say I start off with this acid, and let's say, let me just do this alcohol here. We'll do propanol. Okay. So again, what's going to happen is this bond here is going to break, and the hydrogen and oxygen bond is going to break. So the hydroxide ion and the hydrogen will form water, and then the bond is going to form between the oxygen from the alcohol and the carbonyl carbon. So what I'm going to end up with is, let me move this over a little bit, is this compound here. Remember, the rest of the molecule is going to stay intact. The only thing that's happening is I'm going to have to move this over. The molecule itself is going to stay intact. The only thing that's going to happen is this group is going to be replaced by this group here. Now, you will want to practice these reactions. Esterification, the reaction of a carboxylic acid and an alcohol. Ester hydrolysis is another one that you need to know. So we start off with an ester, and we have water, a strong acid catalyst, and look what happens. This is just the reverse of esterification. So what's going to happen is this bond here breaks, okay, and this bond here is going to break. The hydrogen is going to go to this part of the molecule, so it will bond to the carbon or the oxygen there, and then the hydroxide will bond to this carbon here. So what do we end up with? We end up with our alcohol, okay, and the acid back. So hydrolysis of an ester is just the reverse of the esterification reaction. Again, we do need a strong acid catalyst for this reaction. Well, I was going to talk about saponification, but we won't discuss that until we get into the biochemistry, so do not read about saponification. I do want to talk to you about polyesters, and I think everyone's heard of polyester. These are polymers, and what it takes is a diacid and a dialcohol, and they react in order to yield the polyester. There are different polyesters, but here's one example. They take terphthalic acid. Notice it's a diacid, and they react that with ethylene glycol, which of course is a dialcohol, and it undergoes the polymerization reaction in order to produce the polyester. So this here would be a repeating unit. So the actual polymer would be made up of thousands or hundreds of thousands of these repeating units. Okay, so again, the whole idea would be a diacid and a dialcohol, and they undergo a polymerization reaction to produce the polyester. I do want to talk about phosphoric acid and phosphate esters for a few minutes. So we already know what phosphoric acid looks like. This is the formula for phosphoric acid, and it has 3 ionizable hydrogens. So it can form this. It can form this ion, and of course phosphate ion. Okay, so it forms 3 different ions: dihydrogen phosphate, hydrogen phosphate, and phosphate ion. So just like carboxylic acids, phosphoric acid can react with an alcohol, and it forms what we call phosphate esters. So it could be esterified at just one group, or at 2 of its groups, or at all 3 of its groups by reacting with an alcohol. So here we show the structures of the phosphoric acid and then the 3 anions. So let's take a look at what a phosphate ester is. So for example, well, first, a phosphate ester is a compound formed by the reaction of an alcohol with phosphoric acid. So we might end up producing what we call a monoester, a diester, or a triester. Okay, so here we have a phosphorus bonded to 3 OH groups, and then this double bond here, okay, between the phosphorus and the oxygen, and that reacts with an alcohol, and just like a carboxylic acid. So here, rather than a carbon, we have a phosphorus that has a double bond to an oxygen, then a single bond to this alkoxy group. Okay, so this would be the phosphate ester part. Okay, this is a monoester because we only have one such group. And here we see a diester. So, like, for example, this would be considered the phosphate ester group, and this would also be considered the phosphate ester group. So you have the phosphorus, single bond to this alkoxy group here, and then the phosphorus oxygen double bond. And then, of course, here we have this triester, so a phosphate triester with 3 such groups. A little bit later in biochemistry, we'll see how important these are. If we have 2 molecules of phosphoric acid and they combine to lose a molecule of water, they form what we call a phosphoric acid anhydride. So that will react with another phosphoric acid molecule in order to give triphosphoric acids. So these acids can form esters, and these esters are known as diphosphates and triphosphates. So again, so we have 2 of these molecules, and notice that there's an oxygen here bonded to 2 phosphorus atoms. That's a diphosphoric acid. Here we have 1, 2, 3. So that's a triphosphoric acid. Okay. So what we're interested in, what we will be interested in, is the phosphoryl group. Notice the 3 oxygens here. So we're going to be talking about a reaction later on in biochemistry called phosphorylation. Okay, and that's where one of these phosphoryl groups is transferred. It turns out that in biochemical reactions, these phosphoryl groups are provided by ATP, and that's converted to adenosine diphosphate, or ADP, in a reaction that is accompanied by a release of energy. So we'll talk about both ATP and ADP in the biochemistry portion. I'm not going to go into this in any detail, of course, here, but just be aware that I want you to know what these phosphate esters look like. I want you to know what the phosphoryl group is. And again, don't worry about the phosphorylation reaction now. We will talk about that much later on. So this ends chapter 24. Again, just focus on the reactions that I talked about in the video. As far as the preparation of carboxylic acid, your book goes into a little bit of detail, but remember, we know that aldehydes, when treated with an oxidizing agent, will produce carboxylic acid. So that's the only depth that I need you to go into. So have a great day. If you have any questions, please contact me. Bye-bye.